Okay, so here we go. Let's talk about kidneys and the whole renal system, okay? But before we start on that, since it's official class time, I just want to bring up the fluid electrolyte pH quiz thing as homework, or homework as quiz, whatever. I just want to make sure everybody's clear that you do the homework on whatever time it takes you to do it. Go for it. But then you've got to transcribe it into that thing that's on the calendar, okay? Because that way you'll get the feedback. Otherwise, because I can't grade a paper and give it back to you, and that's very frustrating. So I figured out how to create this in that system. So hopefully it makes sense. Just fill in your answers, and that way when you submit it, it'll grade it. It'll tell you what you, it will, oops, hold on, I got to get Shelly in here. So it's it'll show you what it is that you missed and what the right answers were, okay? So hopefully everybody's got that figured out, because that's due up on Thursday, right? Okay, cool. And then what we were talking about, if you came in a little late to the game, was the frustrations of this honor lock thing. And I'm sticking with until we get to the last test, so test 4 in the lab, and the test, or the exam 4, and the cumulative final and lecture. I ain't even messing with it. I'm letting my colleagues get it all sorted out, figured out. If you have other problems, then what I've already heard, I heard it slows the system down when you do honor lock, and that scanning your ID, you've got to do your student ID, because the driver's license one is too shiny. But otherwise, I'm going to report that back to my colleague and say, okay, here are some issues. But if you come up with other stuff in another course or whatever, please let me know so that I can share it. Okay, y'all? We good? Okay. Chelsea popped out. Chelsea popped back in. Okay, cool beans. All right, you ready to talk about kidneys? Let's pee. To pee or not to pee? Here we go. All right, so in your books, we're on page 975. Okay. So let me scooch my book over here so I don't have to do too much looking away. Oh, and when you do honor lock, don't look away from the screen. Tatiana said, oh my God, it freezes everything up on you. So even if you think off in the distance, you have to think vacantly facing the screen. Oh my God. All right. So the urinary system, you came into this course knowing that it's all about making urine. There's no question in my mind. Everybody knew it was about pee, right? But we've met a bunch of other stuff. I mean, in the first chapter, right, we met about erythropoietin. So we know the kidneys play an important role in red blood cell production. So certainly, yes, urine is to eliminate the organic waste, or urea or uric acid, but we also know that it's really important for maintaining our red blood cells. We also know that it is involved in blood pressure, right? Because we also know from the blood vessel thing, I'm talking about blood pressure, about the renin, angiotensin, aldosterone. If you guys don't know that, by the time you leave this course, I'm going to have to hunt you down. Honestly. Okay. Of course, it also determines how much water, right? Because we know renin, angiotensin, aldosterone. Aldosterone makes us reabsorb what? Quick. Sodium. And then what follows sodium?
Water.
Who let the water in?
Salt.
ADH.
Sodium is salt.
Okay, so anyway, so ADH. So we're certainly regulating the amount of water that we retain versus secrete. We're regulating our electrolytes, because we're regulating sodium. And when we regulate sodium, remember, whatever sodium does, potassium does the exact opposite. We're also going to determine what we do with excess calcium, chloride, those things. So your kidneys are determining which electrolytes we're holding on, what we're getting rid of. So anyway, the kidneys are located retroperitoneally. So the left one is a little bit higher than the right. Any idea why?
I'd imagine it's being pushed down by another organ.
There's a great big organ right in here. What is that organ?
The liver.
Yeah, the liver's in the way. So the right one has to be lower. Okay. So when you look at the kidneys, okay, they're hanging out behind. So this is why, you can be a kidney donor, a living kidney donor and they'll take it, but they're coming through your back. So it's a really big deal to donate a kidney. Plus, you better take really good care of the kidney you have left. All right. It's also why when you look at where they are from the back, whoops, from the back, said she, you can see that those floating ribs, the 11th and 12th ribs, those are the vertebral ribs, they're actually protecting them. And so when I teach A&P1, I talk about when you remove these lower ribs to make you look more like Barbie because they're stupid people and unethical surgeons. Like Bo Derek had that done. I don't know if y'all know who she is, and Linda Evans. There was something to share. I think they had their ribs taken out, their lower ribs, which means their kidneys are not protected, which is just crazy. All right. So anyway, so if you look at the packaging of the kidneys in your books, this picture is over on page 976. So outermost around here is the renal fascia. The renal fascia's job is as a dense fibrous connective tissue, and it covers the kidney and the adrenal gland. It's really just there to anchor the kidney with its adrenal into place. All right. Then around that, inside that renal fascia, there's an adipose capsule. That's a big deal. One of the things that happens if people starve, like an anorexia nervosa, or if they're just literally starving because they don't have any food, is that they lose their adipose capsule. And when they lose that, then the kidneys actually will drop. They will droop. It's called ptosis, which is actually spelled Ptosis. It's a drooping. Okay, so if you droop and you look at how these guys are set up, if you look at your kidneys, if I lose my adipose capsule and this now drops down, if the kidney drops, it'll kink the ureter. That's the exit tube, right? So if you kink the ureter, you're going to still keep making urine, but you won't be able to drain it. And then you get something awful. It's called hydronephrosis. And hydronephrosis literally means water kidneys, water nephrons. So urine backup in the kidneys, and it will kill them. And you'll end up with renal necrosis. When you see necro, I want you to think death. So we need to have some fat around our kidneys. You need to have a certain amount of body fat or things go bad. Not only do your eyes sink back, but your kidneys may droop. So you got ptosis. All right. Everybody cool? So far, so good. All right. All right. So back to this picture. So then inside the adipose capsule, which is my nice cushion and holds it up so we don't kink our ureter, we have the renal capsule itself. So the renal capsule is that dense, irregular connective tissue that goes around the outside of the kidney, okay? So it is a fibrous, tough thing, and it reminds me a whole lot of what's around the outside of a kidney bean, okay? So if you boil any kind of kidney beans, any of those beans that you can dry and reconstitute and boil, and you see the, just like peas too, the shell of it, that's kind of what this is like. It's that fibrous capsule around just the kidney itself.
The renal capsule and the fibrous capsule are the same.
The renal capsule is the fibrous tunic. So it's a fibrous capsule. Yeah.
Okay.
Okay. It's just dense, irregular connective tissue. So it's tough stuff.
Okay.
All right. Then some other things that are just quickies because they're familiar, or they're supposed to be. A hilus is an indentation where things come and go. So the renal hilus is this area here where you've got the renal artery coming in, the renal vein draining, and you've got the ureter leaving, okay? The space where all this tube system sits, because we've got the calyces, which are cups, and they're leading. What? We good?
The sinus.
Is the sinus. The sinus is the space, okay? So when they talk about the renal sinus, you're never going to just see a space because it's filled. It's filled with the ureter, the renal blood vessels, the lymphatics, nerves, the renal pelvis, all that stuff is in there, okay? So you're not going to see it, but it's that space that they're sitting in is basically what it is. You know, cortex is outer and medulla is inner. That is not news. The thing that's interesting is what is in the cortex and versus medulla. So in the medulla, you've got these dark red, brown, triangle shaped things. These are the renal pyramids. And when you look at the renal pyramids, they look like they are striped. And the stripes all lead towards this pointy thing, which is called the renal papilla, because a papilla is like this nipple thing. We met the duodenal papilla, right? The major duodenal papilla. Okay, the reason all these look striped is because what they have in them is these tubes that run straight up and down. They've got loops of Henle in there, and they've got collecting tubules. So all of this stuff lines up, and that's why they look striped. In between the pyramids are these renal columns. They are cortical material that just comes down between the renal pyramids. Okay, so that's kind of the welcome to of those parts. Now, here's the deal. The functional unit of the kidney is the nephron. We're going to look at that shortly. But when your blood is being pushed through a glomerular capillary bed, and we've got all this filtrate that we're going to reabsorb most of it, and then whatever's left becomes urine, the drip of urine forms right at the renal papillae. Okay, so each of these little nipples sticking in is sticking into a cup. So they each have their very own cup that the drop of urine drips into. That cup is called a minor calyx. Okay, so calyx literally is Latin for cup. So the minor calyx catches the drip of urine, which then flows to a major calyx, which is just saying, I have more than one minor calyx contributing here. Okay, so major calyces are made up of more than one minor calyx. Then all of the, What?
I think that's feedback.
Okay. All right. So the renal pelvis is kind of the final funnel before we leave the kidney. And then when we leave the kidney, we go out through the ureter. Okay. Inside the walls of all these calyces and the pelvis and the ureter, you have smooth muscle who causes peristalsis. It's why, you know, I could say, okay, everybody, drink this entire big jug of Mountain Dew, which is, I gather, loaded with caffeine. So drink it, and I'm going to hang you by your toes. And if I did, you would still fill your bladder. It would get very messy later, because unlike with feces where you can keep compacting it until you got wood putty in there and the fecal impaction, yeah, no, this stuff, you fill your bladder to a certain point and you will urinate. If there's a real blockage, you'll rip your bladder. It will tear. So it's a serious thing when a guy gets a blockage, because the guys are the ones who tend to get that, girls not so much. Okay, we'll get to that later. All right, so far so good. Okay. So now let's look at the blood flow. So in your books, if you flip over to page 978, you'll find this. You need to know the flow in, and once you know the flow in, you pretty much know the flow out, okay? So off the aorta, we know we've got our renal arteries. We met that in the blood vessel chapter. So the renal artery comes in, it branches into segmental arteries. So the first branches are the segmentals. The segmentals then come up and they become interlobar. The interlobars are running up these renal columns. Okay, so the interlobars then become an arcuate. Well, arcuate certainly makes sense because it's arcing. So the arcuate arteries then become these things that radiate out into the cortex. So they have the name of either interlobular or cortical radiate. Okay. All right, you might need to mute if you've got your usual thing going on there, Miss Shelley. All right, so the cortical radiates are the ones that are the same thing as the interlobular, okay? So the longer the name, the smaller it is. It's sort of like calling somebody Patty instead of Pat, all right? Makes you diminutive. So once we get into there, then we get into the details shortly when we talk about the actual functional unit of the kidney, the nephron. So glomerulus or glomerular capillaries are going to, all this stuff we're going to look at in the nephron. So After we leave that, then we start looking at the flow back, looks just the same. So we've got the interlobular veins or the cortical radiate veins, which lead to the arcuate veins, which lead to the interlobar veins. But instead of having segmentals, we just go straight to form the renal veins. So we skip segmental veins. They're only segmental arteries. And then back we go. So we have gone through, we have pushed our plasma through. Everything that is small enough to get through the filtration membrane is going to be pushed through. Then we've picked back up most of everything before we ever leave, and then we come back out through the vein. So these kidneys of ours are extremely impressive. They are shoving through this plasma. They're creating this filtrate that is urine going to be, if we stay inside the tube system, come out the renal papilla. But an incredibly large percentage of what we shove through and make into filtrate, we suck right back in. But we've left the stuff we don't want to reclaim in there. We also secrete stuff that we want to ditch, like some drugs get secreted, protons, so we can adjust pH. That stuff will all get secreted, okay? But you don't shove out as urine most of it, you reclaim most of it, okay? Good so far? All right.
May I ask a question?
Sure.
Glomerulus, it's a part of nephron,
Yep.
and it is located in cortex, right?
Yes.
Somewhere it's invisible, something really tiny, invisible. So
they are very tiny. Yes.
Okay, so I cannot even discern it.
You can see it in the microscope, but you're not going to see it by just looking.
Okay.
No naked eye stuff.
Okay, gotcha. Okay. Thank you. So this is like from the afferent arteriola, it's coming to the nephron, right?
Right. All this is tiny, right? So see this box over to the right here? Mm-hmm. That's all inside the nephron. That's tiny.
Gotcha. Thank you. Thank you.
They're all tiny. Okay. All right. So the nerves supply to this. When we're talking about the kidneys, we're really talking about blood flow. And so therefore, we're really talking about sympathetic nervous system. Parasympathetic is not really in charge of blood vessels. So therefore, this is all about the sympathetic nervous system. So we have actually some vasomotor fibers that regulate blood supply to the kidneys by vasoconstricting or vasodilating those renal arterioles. So these little guys here, the afferent arteriole mostly, but to some degree the efferent. These are the ones that are tiny and they're right by they're leading into the nephron. These are what the sympathetic nervous system works on. Okay, so if you really kind of think of things as a hose, right? This is hose. The more we let flow through, if we vasodilate, we're letting more through, then you've got bigger flow, that's bigger pressure on tiny walls, which means that I'm going to shove more fluid out, right? Because there's just higher pressure. So this is really straightforward stuff. That's why, we can kind of go zip through the urinary system because it's just pretty close to intuitive. All right, so let's get down to the nephron part because these are cool. These are the functional unit of the kidney. So in your books, this is just on page 979. All right, so what Tatiana was talking about is that you've got an afferent arteriole that comes into a capillary bed called the glomerulus, and then you have an efferent one leaving. What I want you to notice on this picture is that look at the one going in, the afferent, A for admit, versus the efferent, the E for exit. See which one's bigger? Can you tell? Afferent. The afferent one is bigger. Think about it. If I'm trying to build up filtration pressure, it makes sense to have a bigger tube coming in and a smaller tube leaving. I want pressure because it's that filtration pressure that's going to cause the plasma to be forced out of the capillary bed, the glomerulus, and then become something that I can now work on, okay? The processing can happen. I call it filtrate, all right? So anyway, let's look at these parts now. So this part right here is called the renal corpuscle. It's that combination of the proximal most end of the nephron and this blood vessel bed. So the glomerulus and the Bowman's capsule. So I'm going to move to a better picture of, nope, not that one. Keep it going. There we go. I'm going to focus for just a moment at the proximal most end of the nephron. This is the renal corpuscle, which consists of the glomerulus, which is the capillary bed, and that is fed by the larger afferent arteriole, and it has the smaller efferent arteriole leaving. And then this is inside this Bowman's capsule, or glomerular capsule is another name for it. Well, the thing is that this Bowman's capsule is built just like our parietal and visceral membranes thing, okay? Only it's on a tiny level. So if I think of my heart as, you know, I've got my balloon, I'm plunging into my balloon, I've got the visceral layer on the right next to the surface, right? And I've got the parietal layers outside, and I've got a capsular space, right? Or the pericardial space, right? The cavity. Well, in this case, what happens is that, and everybody found this in your books, right? This is over on page 983. So what happens in this case is that the Bowman's capsule is built sort of like it was a balloon. And so the outer part is the parietal layer of the Bowman's capsule. But this visceral layer is very specialized cells, and these cells are called podocytes. Podo means what to you? If you go to a podiatrist, who are you going to?
Legs, foot.
To the feet. Yeah, podo is foot. So this is a foot cell. It's the visceral layer of the Bowman's capsule. And what it has is all these little pedicels. That's what the toes are called. So these little extensions are called pedicels. So the pedicels of the podocytes interlock. And when they interlock, they have spaces in between them, okay? And those are these filtration slits. So like if you took your fingers and you just opened your hands and you interlocked through, slid fingers into between each other and kind of then stretched them out, you can see gaps between the fingers. Those are the filtration slits formed by the pedicels of the podocytes. How's that? So the foot processes are the pedicels of the podocytes, which are the visceral layer of the Bowman's capsule. So that's the nomenclature there, okay? All right. So then that means that between the visceral layer made up of pedicels of podocytes, then we have a capsular space. This is where the filtrate first is formed. So if I am blood coming in through my afferent arteriole and I am being pressured against the walls of these capillaries, I'm going to leak through the capillary wall, through the basal lamina, through all of the space, and then I will have to be small enough still to get through the filtration slits between the pedicels, the podocytes, and then I find myself in this capsular space. Good so far? Okay. All right. So then what we do is from there, and I'm going to back up a little bit because I can. So can you? Is I'm going to go back to that previous picture. And then what happens is as the filtrate is being formed, so this is it just was plasma before it got shoved through. So it's basically plasma minus, there are no formed elements because they shouldn't be getting through. And there aren't proteins because they should be too big to get through. Okay, if I start seeing proteins, I worry. It's not good. I don't want really foamy urine. I worry. Okay. Probably means my pressure is way too high and I've just put so much pressure that the capillary walls expanded too much and the filtration slits expanded too much and I got big stuff through that I shouldn't have gotten through. All right, so anyway, so as I come into my capsular space, I immediately am going to start leaking out of there because I have a tube. This is my proximal, because it's closest to the beginning, convoluted because it's twisty, tubule. Now, here's the thing about this proximal convoluted tubule. when you think about, if I have glucose going through there, oh yes, I do. Amino acids, yep, they fit too. Vitamins, minerals, lots of water. So I got stuff shoving through that I really would like to keep, right? Why would I have absorbed all this stuff and then just send it out in the urine? That's stupid, right? Now, there are going to be things I send through if I just can't reclaim them. But so you have a philosophy in your body that says, grab it quick before it gets away from me. So the grab it quick before it gets away from me is done by this proximal convoluted tubule. If you kind of think of it as like a conveyor belt, and I'm old, so what pops in my mind is there was a show called the Lucille Ball Show, and Lucy and Ethel were working in a chocolate factory, and things were on a conveyor belt. And so even if you have no idea what I'm talking about, picture two crazy women who are best friends who are off the chain, and they're trying to, they got their, bouffant hats to keep their hair out of the way, and they are on this chain, and they're supposed to, their job is to get the chocolates arranged in the box, right? And then it moves along. But something happened and the conveyor belt went faster and faster, and eventually everything all goes to hell in a handbasket, right? And they're shoving chocolates in their face. It's very, very funny, but I think about a conveyor belt. And, if I'm sending something through and I really want to get it back, I'm going to do it sooner than later because it might zip off, right? So this proximal convoluted tubule of ours is where we're going to do the vast majority of our absorption of all those things that we want to keep, okay? We also secrete some stuff. We say, yeah, you know what? It's too acidic in this body, ditch some protons. So there are things that we secrete there on purpose to get rid of, including drugs. But the big thing about this one is this is my get it back before it's gone part of my nephron. Okay, so that's my proximal convoluted tubule. Then I'm going down and up. This thing here is called the loop of Henle. It's also called the nephron loop, but I'm a big fan of, if some dude figured it out, they get to keep their name on it, because as long as I'm alive, I'm going to give them their credit. So I tend to call it the loop of Henle. Although nephron loop is absolutely correct, I tend to keep with the giving credit where credit is due. So two things right now about this. One is its function is salt and water reclamation. The loop of Henle is really where we determine how much we're going to pee out, honestly. It reclaims salt and water, okay? We have drugs called loop diuretics like Lasix and Bumix that we give to people if we need to get a whole lot of water off them really fast. So they work on this, because if you interfere with this, you will interfere with our ability to reabsorb water and salt, okay? Because that's really all it does. So the other thing about it is, when we get to the how does this work, is that all loops of Henle, hear that absolute? We don't have very many absolutes. All loops of Henle are found in the renal medulla. All of them, always, okay? It's part of how they work. So remember those stripy looking renal pyramids? This is part of why they look stripy, okay? All right, so I go down the descending limb of the loop of Henle, I go up the ascending limb, I've reclaimed water, I've reclaimed salt. They help each other reclaim each other. We'll get to the details because it's really, really cool. It's very, very clever. And then we get to the distal convoluted tubule. So it's twisty-turny, but it's after the loop of Henle. This is back up in the cortex. The distal convoluted tubule is the tweaking part. Remember aldosterone, remember ADH. This is where they work. They work at the distal convoluted tubule and they work at the collecting duct. Okay, this is that final assessment of, do we need to hold on to more or less of the water and electrolyte world? Okay, that's where we're working with those. That's where our receptors are for that. Okay, cool so far? All right, so now when we are getting to this final part where we do that final tweaking, we better have an idea of what we need to do. So that then goes to the juxtaglomerular apparatus. So right here, And this is back to page 983. All right. This thing right here, it's called the juxta because it's next to glomerular because the capillary bed, juxtaglomerular apparatus or complex. It's made up of two different parts. One is these macula densa cells. Okay, and what the macula densas are they are cells whose job is to be detectors. They are detecting they're chemoreceptors. So how is the concentration? They're checking the osmolarity. That's their job. Okay, so what's going on? They are actually part of this distal convoluted tubule. So it's that last filtrate. They're paying attention. What's the osmolarity in here? Okay, the other part, the juxtaglomerular cells, these are part of the arteriole. So these cells, this part of the wall right here glued to the afferent arteriolar wall, these are the ones who are mechanoreceptors, and they produce the thing that you've already heard of, renin. They also produce erythropoietin. So these are the ones that put out the, I need to raise my blood pressure, I need to increase my oxygen carrying capacity by putting out the hormone erythropoietin. Okay, everybody good? Okay, got to know the job function. So macula densa, they're just monitoring what's the osmolarity. Do we need to hold on more or not? And then the juxtaglomerular cells, the JG cells, these guys are the ones who are secreting. Okay, based on what's my pressure like. Okay, all righty. So now types of nephrons. Let's see. Let me go back to this page. Whoop, whoop, right there. There are two different types of nephrons. This is over on page 981. So I'm flipping around on you. All right. So but I promise I'm following your outline. I did bring that with me and I put it in front of me, so I'm not going to jump too much in your notes thing, okay? My brain does jump a bit, but I'm promised to stay here. All right. So when I look at the types of nephrons, there are two different flavors you'll see. You'll see cortical, these are the littler guys, and then you'll see the juxtamedullary. The vast majority of our nephrons are cortical. They're probably about 85% of our nephrons are cortical type. Only about 15% are the juxtamedullary, but the juxtamedullary are the ones with the incredibly long loops of Henle. So these are the guys who are incredibly important in concentrating urine, okay? Because that loop of Henle is about concentrating urine or not. All righty? Okay. So now let's go back to our glomerulus. Let's see. Nope. I lied. I think this is still my best one. This is the best I can do. All right. So here we go. We've come from our cortical radiate or interlobular arteries. We come in as an afferent arteriole into our glomerular capillary bed. When we get into there, then what's going to happen is as we squeeze out, so I'm going to flip back again, as we squeeze out into our capsular space, we get the filtrate out, right? Two things have to happen here. One is I've got to leave through my efferent arteriole whatever is left. But whatever it is that's come into my capsular space, and then it's going to flow down my proximal convoluted tubule, down my loop of Henle, up, around, through my distal convoluted tubule. Everything I pick up has got to be brought back to blood. Okay? So in order to do that, I have to be surrounded by capillary beds. So there are a couple different types of capillary beds. So when you leave the efferent arteriole, the kidneys are very weird because instead of what normally, right, we have an artery, an arteriole comes into a capillary bed, then we have the post-capillary venule, don't we? Isn't that our normal way? Remember that? In this case, we have a post-capillary bed arteriole again, because that's an efferent arteriole. This is not about oxygenation. It's not about exchange of things. This is about a filtration bed. So this efferent arteriole then becomes another capillary bed. And this one is truly a capillary bed. And its job is to pick up anything that we reabsorb. You'll see resorption and reabsorption. It's the same idea. It means that whatever we are trying to reclaim when we come through this proximal convoluted tubule, when we come through the distal convoluted tubule, these are all going to be picked up by going through the tubule walls and getting into this convoluted capillary bed that's called the peritubular capillaries. Everybody good? When I say I'm resorbing or reabsorbing from the filtrate by this nephron tubule system, I am saying it has to be getting back into blood, or else what am I doing with it? I'm resorbing it and just putting it out in the interstitial spaces? That would make no sense, correct?
Excuse me, could it be like a vasa recta, this
We're not
place?
there yet. We will, not yet. Okay, hold on.
Because I studied the chain, and after efferent, the pathway goes to the vasa recta.
It does. It does that too. Okay.
I want to say that after efferent, it's gonna go to the capillary beds.
There are two different kinds of capillary beds, Tatiana. So part of them are these peritubular capillaries, whose job is to pick up what's being reabsorbed in the convoluted tubules, okay? But next we get to the other ones, okay? Ready?
Thank you. Sorry, I found that peritubular capillaries, they are vasa recta. It's another name.
They're different, okay? It's very important, okay? So hold on. So vasa recta is another branch of the capillary beds, but their job is only to reabsorb from the loops of Henle. That's it, okay? And these are very important because they have a very distinct flow pattern. So they look like a rope ladder, okay? But they're called vasa recta because they are up and down, because they are following the loops of Henle up and down. All right?
So when it's in the medulla, it's vasa recta. When it's in the cortex, it's peritubal capillaries, right?
Right, because in the vasa recta are following the loops of Henle, which are in the medulla. The peritubular capillaries are around the proximal and distal convoluted tubules because they're in the cortex. Okay.
Gotcha. Thanks. Yeah, that makes sense.
Okay, cool. All right. And we're going to get into the details of how important the vasa recta are in just a few. Okay. So, but I'm trying very hard to stick with our outline so that I don't lose you. All right. So let's see. So talking about, oh, and by the way, these peritubular capillaries will dump into the interlobular veins or the cortical radiate veins, whichever one you call them. Either one's correct. Okay, so here's the thing. We are shoving through our glomeruli. We're shoving probably a little over a liter through our glomeruli every minute. Okay, a little over a liter every minute. Think about that. Okay, so what we have is our initial filtrate is basically, think of it as plasma without the proteins. But at the end of a day, assuming that you are moderately hydrated, that you have not just had like a cup of coffee in the morning and then good luck to you the rest of the day and your mouth is parched and everything's desiccated, at the end of a day, you should put out probably a little more than a liter, probably maybe 1.5 liters of urine in one day. So think about the incredible efficiency of reclaiming that we're doing. And it's all going into those peritubular capillaries and the vasa recta, okay? So what we're trying to do is reclaim everything we want to keep, but ditch the metabolic waste, the stuff that we don't want, or the things that maybe we just couldn't reclaim, although we would have loved to, like, oh, I don't know, if you have elevated blood glucose levels and you just can't get them back because you basically exceeded your ability to have enough carriers. All right, so let's move into our.
I'm sorry, quick question.
Uh-huh.
You said we're taking in a liter a day, but we're putting out more. So
No, I'm saying that through each of the capillaries, through all these, we're getting feedback here, right? So when we're feeding blood into the kidneys, every minute you're putting through about 1.2 liters of fluid.
Oh, okay. So a minute
blood
versus the end of the day.
But
I got you.
The day, 24 hours, which is 24 times 60 times, right?
Understood. Okay.
Okay.
All right. Thank you.
You're welcome. Okay.
Okay.
All right. So now we need to talk about this whole process of filtration. All right. So moving to this and this. I like this one. Okay. So this is over on page 984. You realize how close we're getting to 1,000. Holy moly. All right. So hydrostatic pressure pushes filtrate through the glomerulus. This is filtration. It's the same principle if you have like a French press to make your coffee, right? You put the grounds in one side with the hot water, then you press so that you keep the stuff that shouldn't go through the filter. That would be the coffee grounds. In our case, it would be the proteins and the formed elements in the blood. And then you put pressure on it, and only the liquid part is what gets through. So what it's getting through is called the filtration membrane. So these are physical barriers for anything that is a size thing. It's really about size. So remember, the capillary beds in the kidneys are fenestrated capillaries. In other words, they have those membrane covered pores. So they're leakier than our standard continuous capillaries, right? Okay, so we have to if we're going to get through, we've got to get through the endothelium of this fenestrated capillary. So we get through that little portal of thin membrane. We've got to get through the lamina densa, which is that basement membrane that those endothelial cells of the capillaries are sitting on, which won't let big plasma proteins through. Okay, it lets little things through, all those nutrients that we have absorbed. We've got the pedicels, the podocytes, making those filtration slits. Okay, so all this stuff should only allow the small stuff through. It's important not to let those plasma proteins through because remember, we need those for our oncotic pressure too, right? They're carriers. There's a lot of stuff those plasma proteins do. We really don't want them coming out. It's a pathology if we have proteinuria. If we end up with protein in our urine, it's a bad thing. Okay. So you got this glomerular hydrostatic pressure, just that physical presence of the blood pressure on the walls of these little fenestrated capillaries pushing through the filtration slits. Okay, so we're forcing through. Now when we're pushing out into this capsular space, what you're also doing is you're going to have some fluid in here that has a little bit of hydrostatic pressure back, but not much, because look, there's a hole. When you go into the capsular space, that filtrate is immediately going to leak out because it's going to head down through that proximal convoluted tubule and work its way out. So there's not a whole lot of back pressure. There should not be a whole lot of back pressure. Okay. So when we talk about pushing things through, this glomerular hydrostatic pressure, forcing the water and the solutes, the small things, through the filtration membrane, what they use in the world of medicine is they talk about the glomerular filtration rate. You will see that some drugs, they want to do find out what the GFR is, the glomerular filtration rate. which weirdly, backwardsly enough, is how I remembered the layers of the adrenal cortex, GFR, right? The zona glomerulosa, zona fasciculata, zona reticularis. It's the GFR. So anyway, so glomerular filtration rate is the total amount of filtrate that's produced per minute by the kidneys as a whole. Okay, so they look at GFR, glomerular filtration rate. And the way we control our glomerular filtration rate is by controlling the blood pressure to the glomeruli and in the glomeruli. Okay, that makes sense, right? You want to shove more stuff through the hose to increase how much leaks out of the hose. Back to those soaker hoses in the garden. If I turn up the volume I shove through, I increase the pressure, it's going to start spraying bigger. Okay. All right. So how do we control this stuff? Well, the way you're going to control it is we've got intrinsic stuff going on. So we can control inside there the vasoconstriction, vasodilation of that afferent arteriole. We do the efferent a little bit, but not as much. It's mostly about the afferent arteriole. So you actually have just smooth muscle here that when it gets stretched, it reacts by contracting. Okay, it's just that's happening right there. Mostly it's going to be about the sympathetic nervous system saying, okay, if I am stressed, then I am going to release epinephrine, right? That's that adrenaline, oh my God, fight or flight, gonna die. If I am stressed, what do I want? More blood pressure or lower blood pressure? Higher or lower? Thumbs up, thumbs down. Up.
Higher.
Higher, of course. I'm jacking up, right? So as I want more pressure, do I want more or less fluid retained? What do I want? More volume or less volume? More urine or more blood?
More blood.
More blood.
More blood. So I got to hold on to the urine, right? I got to hold off of making urine. I got to hold on to the fluid. Everybody agree? That makes sense? Okay. So the way to do that is to make sure that I don't have too much pressure coming into the pipes, right? So I'm going to vasoconstrict with my sympathetic nervous system, because what that does is it slows down, it decreases that hydrostatic pressure, and therefore it slows down how much of the filtrate is formed. Everybody with me so far? Which means that my convoluted tubule has more time to reclaim more. My loops of Henle and my distal convoluted tubule have time to retain more. I have slowed down my conveyor belt. I don't have to fling chocolates on the floor and stuff in my mouth in order to be okay. I can do my job and reclaim everything, which means that I hold on to more water, which means that I have better blood volume, which means that I have more pressure in the pipes, which means my pressure goes up. We good? The logic stream good? Everybody? Okay. All right. So epinephrine causes vasoconstriction of my afferent arteriole if I need to hold on. The norepinephrine is going to go and talk to these guys, to the juxtaglomerular cells, and they're going to be told to secrete their product, which is going to increase blood pressure. What is the product that's going to increase blood pressure?
ADH.
No, who makes ADH?
The
Anterior pituitary.
No, who makes it is the hypothalamus, kids.
hypothalamus, and then it goes into the posterior pituitary, and it's stored there, right?
Correct. But right now I'm interested in what do these juxtaglomerular cells make that have to do with blood pressure?
Renin.
Renin, I heard it. Renin. Say it louder with more authority. Renin.
I wrote that down, dang it.
Renin. So renin kicks in the renin-angiotensin aldosterone system, correct? Okay. So Norepinephrine from my sympathetic nervous response will get renin going, which does that whole renin-angiotensin-aldosterone system to increase my blood pressure and water retention. And yes, it involves the ADH because that's what's going to allow the water to follow the aldosterone. And that's all happening over here in my distal convoluted tubules and my collecting ducts. So norepinephrine stimulates the renin, epinephrine stimulates vasoconstriction to slow down the amount of flow through the pipes. Okay, cool. They're working together. It's very clever. All right. So everybody okay with renin, angiotensin, aldosterone system? Have I beaten you enough with it now? Okay, I'm going to have to trust you. It's real hard, okay? But we're going to go through the put it together in just a minute anyway. There are other factors that are involved in regulating my blood pressure besides this direct vasoconstriction and the renin-angiotensin aldosterone mechanism. We do have some things like prostaglandins. I have to bring that up because, of course, you know, I keep saying prostaglandins, you need to know that word. Because prostaglandins, depending on where we are, they can either vasodilate or vasoconstrict. We've got this stuff called nitric oxide. It is not nitrous. That's the laughing gas stuff. Nitric oxide is actually a vasodilator. We've got other things that are released locally. So we have control of local activities of vasodilate versus vasoconstrict simply with the cells that are there. So there are local controls. But the big things you had better know about are the sympathetic nervous system response and the renin-angiotensin aldosterone system. We cool. All right. Okay. Isn't that a cool? I love this picture right here, this photomicrograph. I just think that's really awesome. It's actually an electron micrograph, but anyway. Okay. So, yeah, just great pictures. All right, I want to work my way over to this one on page 988. Join me in the adventure. Okay, so this puts it all together, all right? So my systemic blood pressure, if I want to look at over here with what do I do locally? If I have a drop in blood pressure in the afferent arterioles, then I'm going to have a drop in the formation of glomerular filtrate, right? That makes sense. I just turned down the volume through the pipes. So then what happens is I drop the stretch of the smooth muscle in those afferent arterioles. So therefore they're going to vasodilate. And if I vasodilate, now I've opened up the pipes, so let more stuff through. And so therefore up goes the filtration pressure, up goes the formation, right? Okay. And I will increase my glomerular filtration rate. Over here, if I look at my decrease in glomerular filtration rate, I got dropped my filtrate, I decreased my sodium chloride, and I haven't talked about the Lupa-Henle yet, but we'll get to that. So my macula densa says, let's see. What do I think about the osmolarity? Well, let's see. So I'm going to vasodilate. These are going to increase my glomerular filtration rate. I'm going to increase my urine output. Over here, it goes through the renin system. So once again, my JG cells, my juxtaglomerular cells, if I need to increase my pressure, I will release renin, which goes to the renin-angiotensin aldosterone. Here's angiotensin 2, does two things, vasoconstricts. Got the aldosterone, which lets my sodium be reabsorbed, which means that my water follows. Who let my water follow? Who did it? Who let the water in?
Sodium.
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 ADH.
What hormone? ADH. Yes, I heard it. ADH. Okay. So my volume goes up and up goes my pressure. All right. Does this stuff make sense? That's a good flow chart. All right.
Go over it again.
Huh?
Oh, sorry, I'm not muted.
No, you're not.
I have to go over it a few more times, but
Oh, well, that's fine. We got the page there for you, so that ought to help. Okay. All right. So the next thing that's really helpful in your book after that is this table that kind of goes through. It's over on page 993, and it shows you the different things that are being reabsorbed as we go through. Okay, so big thing about proximal convoluted tubule, you got to know virtually all the nutrients and honestly most of the water are going to be reabsorbed. Okay, reabsorption can be either a passive or an active process. Active means it costs me ATPs, but really that proximal convoluted tubule, I want you to think of it as primarily I am reabsorbing all the stuff that I need to reabsorb. Okay. When I get to the loop of Henle, I really want you to think of it as about salt and water. Okay, salt and water, that's what it is. This is where I determine my concentration of my urine. The distal convoluted tubule and the collecting duct are just about tweaking. I'm tweaking my sodium and chloride. I'm tweaking my water. Okay, so that's really what those guys are about. Now, I want to talk about a couple of cool things with active tubular reabsorption. So I'm going to hang out in my proximal convoluted tubule. Okay, so now let's see. Let's go to, do I have a good picture in here? I don't think we have what I want. All right, so I'm going to talk about things by just staying on this particular table part. All right, so when you look at some special absorption ones, I want to talk about the glucose reabsorption, and I want to talk about something called solvent drag. Okay, so first I want to talk about the glucose because we've already kind of seen this because we've seen what happens when you have hyperglycemia and due to the diabetes mellitus. So if I end up with just a whole lot of sugar in my blood, right? Remember the characteristics. I had the polyuria, right? And polydipsia because I had polyuria. I had polyuria because I had osmotic diuresis. All that glucose could not be reclaimed because there was too much. So I ended up having it go out in the filtrate, which went out into the urine, and water followed the solute of this glucose. Right? So I had glycosuria. All right, so here's the why. And the why is that when you look at the ability to reabsorb glucose, glucose has a specific carrier for it. And so it's kind of like, I think about it, if we were in the classroom, I'd be looking at all those seats with people in it and people not in them. So the ones that don't have people in them are the ones that are available for glucose transport. But every seat that has somebody's butt in it is blocked already with somebody else in it, right? So if you think of those as gates, if you have so much glucose, you can fill up every single gate. And so eventually what happens is the glucose moves past where there are any more gates and it gets to the descending limb of the loop of Henle. There's no way to get reclaimed. So it's a matter of overfilling the gates. And the term for that is called exceeding the transport maximum. So if I have so much glucose that I've exceeded the transport maximum of all those carriers for glucose, that's why the glucose ends up out in the urine. And then water follows that glucose because water follows salt. It's just osmotic diuresis. Does that make sense? We good? Okay. All right. So another cool thing is that in the world of passive tubular reabsorption, we use electrochemical gradients. If you remember that, the electrochemical gradients, electro means I'm following opposites attract. So if I'm positive, I want to go where there's more negative. If I'm negative, I want to go where there's more positive. So that's the electro part. The chemical is wherever there's more of me, I want to spread out to where there's less of me. That's the whole process of just diffusion, right? So when you are transporting sodium, so let's say down here, and I'm doing some major sodium transport, you set up an osmotic gradient. So as I reabsorb sodium over here, then what happens is water wants to follow the sodium, right? Because water follows sodium and other solutes. So the water follows the sodium. So then what happens is the other solutes that are sitting there behind, left behind, say, hey, there's an awful lot of us here now. So it's called solvent drag. It's kind of cool. So when water follows the sodium, it gets reabsorbed. Then what's going to happen is with the concentration of solutes left behind, as they rise, then they're going to follow their concentration gradient and just basically follow out. Does that make sense? Okay, cool. So when we go out, what we're doing is we're heading towards the capillary. Okay, because remember, we're wrapped around by the capillaries. Okay, back up to all the way up here. All right, so, whoops, oh, that wasn't the one. Where's my picture that I want? There. Okay, so when you've got all this, when we're talking about reabsorbing things, remember what we're doing is we're leaving the tubule and we're going to go through the interstitial space to be picked up by the capillaries, either the peritubular capillaries if I'm in the convoluted tubules, or the vasa recta if I'm down in the medulla with the loops of Henle. Okay. There are some substances that will not get reabsorbed, and it's simply because they don't fit. You know, they're too big, or they are, let's see, what have we got here? They are too big, like they're some kind of a protein or maybe some kind of an artificial something that we got into us. They are, there's no carrier for them. They're big. They could have gone through if they had a carrier. They're not lipid soluble, because if you want to sneak through a cell, lipid soluble is the way to go. If you've got a big charge on you, you can't get through. So there are some substances that we don't want to reabsorb because we don't want them. The whole point was to get rid of them, like urea, uric acid, creatinine. As a matter of fact, creatinine, which is a great big non-soluble, non-lipid soluble thing, it's something that we actually use to determine something called creatinine clearance. And we can figure out how well are your kidneys working by looking at your creatinine clearance. What we'll do is a 24-hour urine, which means that we start the clock. We make you empty your bladder, and now the clock starts. And then every time you urinate for the next 24 hours, and then at that next, when the 24 hours is up, we make you empty your bladder, whatever's in it, and that is your 24 urine output. And we can see how well are they working. How much are you putting out versus how much did you put into your body, and how much creatinine is in there. What's your creatinine clearance? So that's a test that's used here. They have to keep in brown jugs on ice. Some people have done it at home where they're peeing into a jug and sticking it in the fridge. That must be an interesting thing for whoever goes into the fridge. And if you forget to tell them, no, don't go into the brown container, honey. All right. Does this make sense? Good. All right. So other things that we do besides just not reabsorbing stuff that won't to get rid of is we do secrete things. So we will secrete things like the potassium. Remember, when we've got aldosterone, it's hold on to sodium or ditch potassium. We can ditch protons in order to help with our pH. There's some other things that we can purposefully secrete, okay? So they're important in getting rid of things like drugs. It's very important, secretion of just getting rid of drugs, things that we don't want to keep. And it's huge with making sure that we keep our pH and our electrolyte balance, particularly the potassium. Okay. All right. All right, let's see. So now, none of the pictures in your book make me happy when looking at the countercurrent mechanism. There's not one that works well as far as I'm concerned. This is where I'm desperately missing drawing. So the best that you have is this series of pictures that starts on page 996. Okay. So what I want you to kind of try and visualize without me to draw is, let's see. All right. I'm going to go with this picture first. All right. Here's the big picture. Here's Sue's description of the big picture. You ready? All right. What we have going on in our medullary parts of our kidneys, all these nephron loops or loops of Henle, which is what I'm going to call them, the loop of Henle. I've got a descending limb and an ascending limb. So I've got proximal convoluted tubule, then descending limb comes down and the ascending limb comes up, and then I get the distal convoluted tubule. When you look at the descending limb, so the first part, what happens is we reclaim water. Now, what I want you to think about is if all I'm doing is drawing water out, then everything in the tubule is getting more and more concentrated. Would you agree? Because I'm sucking the water out, right? So that's why they're making it a darker color down here. All right, so then we get to this part. And the ascending limb, now we're very concentrated, but we're coming up, and what we're going to do is we're going to start ditching salt. So now we're getting more and more dilute. Can you see how that would be true? Okay, now, so I'm flowing down the descending limb and up the ascending limb. Water is falling out. So I think about waterfalls, right? Water only falls down. Water doesn't fall up. Water falls down. Rain falls down. Water falls down. So water falls out in the descending limb. That's where we reabsorb the water. Salt, if you're superstitious and you spill salt, you're supposed to toss it up and over your left shoulder. So salt is in the ascending limb. You can use what you want. That's how I remembered it. Now, what's happening is that the blood in the vasa recta is flowing the opposite direction. Okay, so the blood is flowing down here. So as the blood is flowing down, it's picking up more and more salt. Can you see that it would? So it's getting more concentrated. Does that make sense? Yes? Okay, so the blood in the vasa recta is getting saltier and saltier because it's picking up more and more of the sodium chloride. Now it comes down here and it comes up, and guess what? It's really salty. So what am I picking up? The water, because water goes to the solute, right? So it's called the countercurrent mechanism, because I've got my filtrate flowing and losing water, getting more concentrated, and then ditching the salt. The blood is flowing here, picking up the salt, getting more and more concentrated, and then it's going to, because it's concentrated, it's going to draw the water to it on the other side. So they're flowing in opposite directions, and that's why it's absolutely imperative that all the loops of Henle be in this same spot, because this is what's going on, is as we go down these limbs, we are collecting water and we are collecting salt, and it's going into the blood, which is going the opposite direction to pick up the salt and then the water. Okay, it's brilliant. It's totally brilliant. It's this osmotic pump that it's just because you got two tube systems flowing in the opposite direction, one picking up from the other, which then makes the other one want to give to the other because there's really salty blood over here, so the water wants to go into it. Really dilute compared to this. Blood picks up the salt because it's more dilute. It's doing this whole osmotic gradient. Tell me you think it's brilliant. Yes? Okay. I just need other people on the geek parade with me, the nerd parade. Okay. All right. So this is huge. All right. This is a really big deal. And so this is why you can see if I have something that's called a loop diuretic and it acts on this, I am messing with my ability to reclaim water and salt, which means that this stuff shines through, which means I am going to lose a lot of water as urine really quickly. You get somebody who comes in with left-sided heart failure and they have puffy feet because they have edema, but they also, their reason they came in is because in left-sided, you back up to the lungs. And when you back up to the lungs, you can't breathe because it pushes the water into that interstitial space and oxygen can't get across it. Okay? So this cycle thing here is trying to explain how the water is being picked up and how the salt is being picked up without drawing the actual blood. Okay.
So a loop diuretic, is that the ADH anti-diuretic, like Lasix and stuff?
Yes, it's exactly. Lasix is one of those. So is Bumex. You'll hear about people who are put on, particularly Lasix. Lasix furosemide is a very, very common diuretic, and it's cheap. We use it with animals too. My mother-in-law has a poodle who is now, she'll be 18 in May, and she's doing really great, but she is on Lasix because she is a very geriatric citizen, four-legged citizen. And so it keeps her going too. So, and we have to make sure she keeps her potassium all right, because when you start messing with this, you also mess with potassium. Okay. Cool, right? All right then. Okay. So let's see. So now we're on to the last little thought, since we've done our major tweaking of how much salt and how much water and how much urine are we going to send out. So then we get to our final stop here. Let's see. So we get to, and all this stuff is on those, the focus figure on 996 to 997. So we get past the loop of Henle, and now we get to the distal convoluted tubule and the collecting duct. Well, remember that the distal convoluted tubule is hanging out right next to that glomerular capsule. And so what you've got is the juxtaglomerular apparatus, which has the osmoreceptors. And they're saying, hey, you know, I'm going to tell you how I feel about our sodium content, our osmolarity, and should we hold on to more water or not? So this is where you get that whole, the antidiuretic hormone, the aldosterone, and it's also where atrial natriuretic peptide, or BNP, ANP, that's where these guys are working, is here. Okay, the collecting duct and the distal convoluted tubule. So aldosterone is making us reclaim the sodium so we can get it back into the blood. Atrial natriuretic peptide is making us less able to reabsorb the sodium. So ANP and aldosterone are direct antagonists, okay? And then we either allow water to follow or not, depending on what we need. And that's our ADH, which is our hypothalamus, who's in charge of everything anyway. All right. How's everybody doing? We okay? All right. All righty. So let's see. Let's move to, all right, renal clearance. I'm jumping down to letter G in your notes thing, because the rest of it, enough. We've got enough. All right, so renal clearance. We look at this, the reason I want to mention this is because it is something that we look at in the world of how are your kidneys doing assays. So what this is, renal clearance is, it's the volume of plasma from which you can completely clear a given substance. It's generally about a minute. So it's a way to determine our glomerular filtration rate and see if there's any glomerular damage. So it is something that you'll see done sometimes. And what they'll do is they give the person a substance that the kidneys have never seen. So there's no carrier for it. So you put it in, it can get out, and you can't reclaim it. Does that make sense? Because it's foreign. It's this stuff that's called inulin. I'm not going to ask you about it, but it is it's a substance. So we look at the other substance to my inulin clearance rate, because I know how much inulin I've given you, so I can use that as kind of my standard to compare how fast are you getting rid of it. So if my renal clearance is greater than my inulin clearance, it means that I'm secreting a substance into the filtrate, like the creatinine. Okay, so they'll look at that by they give you something foreign. It's called the renal clearance. Okay, cool. All right. All right, so let's talk about the urine, and then I'll turn you loose, okay? Because we may as well talk about pee before we're done for today. So the urine, if we look at urine itself, we'll get back to that in a minute. There we go. Okay. Normal urine should have mostly water with some metabolic waste. We agree with that, right? Probably have a little bit of you're going to have some salt. It's going to have some ions, sodium, potassium, phosphates, things like that. So a little bit of maybe some calcium, some magnesium. It's going to have a little bit of the electrolytes. It's going to have a lot of water. It should have plenty of urea, uric acid, creatinine, because those are all normal things to have in there. It may have a little bit of the glucose and some vitamins and stuff. And if you're one of those who likes to take lots of vitamins, the water soluble ones, you just made expensive urine. So you're going to have your C and your B vitamins are going to show up. You take B vitamins, you're going to have beautiful dark yellow, orange urine. Don't panic. You just wasted money on adding vitamins to your urine. If you have the fat soluble ones, you have to worry because fat soluble vitamins, A, D, E, and K, of course, are going to get stored to toxic levels in your liver, so don't go there. But urine itself, does it have a normal color? Is there a normal color for urine? Anybody?
Light yellow?
Yeah, it's a light yellow. They actually kind of call it a straw colored yellow, I guess. But it's yellow because of something called urochrome, which actually came from hemoglobin. Yeah, once again. So we color our feces, we color our urine. It came from broken down hemoglobin. So if you have really dark urine, what's the first thing you should think?
Water.
Drink.
Dehydration.
Yes, exactly.
Drink more water.
Dehydration. Drink more water. Okay. It should.
I have a question.
Yes.
A lot of people say like the more water you drink, like the clearer your pee is gonna be.
Mm-hmm.
Like I drink a lot of water, probably like a gallon a day, and my pee is honestly mostly clear, especially like by the end of the day. It's almost like I'm just peeing straight water. Is that like normal?
Yeah, that pretty much is because you're very dilute. That's the why.
Okay.
Absolutely.
Okay, good.
But the thing is that you can drink too much water. Okay, you got to be careful with how much you drink of water. Okay, so Alex, you probably drink the right amount, honestly, as long as it's got a little yellow to it. Most of us, especially, we old raisins, we definitely don't drink enough water. So, but be careful because you can get too much water. You really can, and dilute yourself too much. Anyway, so it should be transparent, right? Not cloudy. You would expect that. Should it have an odor? Is it normal?
No, I don't think so.
Yeah.
Yeah, it is. It's got that warm urine smell. If you have any dogs, yeah, there's a slight smell, and it depends on what you eat. For instance, last night I had asparagus. Now,
Somebody needs to mute.
Pardon?
Somebody needs to mute. Everybody just mute when she's talking if you're not talking. Alt A. Michael just figured it out, but it bothers me when I hear her twice. Schumann. Okay.
Yep. Shelly, I think you're unmuted. So make sure.
Alt A, Shelly. Alt A.
Yep, you're the one. Okay. So the you should have a slight smell, but if you consume certain things like asparagus, I know that my husband, he eats asparagus within moments. If he goes and urinates right after eating it, and it shows how incredibly quickly we form the filtrate, and that it's absolutely, asparagine has a smell. Okay, so next time you have asparagus, assuming you eat asparagus, go ahead and save up, eat your asparagus, then quick go pee. See if you can smell it. You can. Okay, I promise. If you have uncontrolled diabetes mellitus, you're going to have acetone, right? That ketoacidosis. So you got that acetone smell. Those are not okay, right? The ketoacidosis, that's not normal. pH, it should be slightly acidic, probably around 6, a pH of 6-ish. Can go from probably like 4.5 normally to about 8. Bacteria hate acid, you want it acidic. So if you are a female and you know the signs of, oh no, I'm getting a urinary tract infection. It's burning when I pee. There's a little blood there. I gotta pee all the time. Oh no. What do, ladies?
Antibiotic.
Cranberry juice.
Cranberry juice.
Yes, look at this. The women know. So cranberry juice, it works for guys too, but women know more because the urethra on a female is about 1.5 inches long, whereas on the guy, it's a whole lot longer plumbing. So girls are much more susceptible to urinary tract infections, along with the other things around in that whole area, but we'll get to that next time. But anyway, so the pH, you want to raise or want to lower your pH rather. So if you're getting a UTI, make sure that you drink a lot of water and cranberry juice so that you're going to acidify your urine. If you are a vegetarian, you're at higher risk because you tend to have an alkaline ash kind of diet. So therefore, vegetarians, vegans in particular, they're more susceptible because they raise the pH of their urine. So it's something to think about. They need to make sure they get enough cranberry in there. There's a thing called specific gravity, which means compared to water, pure water is 1.0000 all the way out. Whereas for us, we should have a specific gravity of a little more than that, like 1.001 to 1.035. So in other words, not a lot of density, but it should have something showing to it. Okay. So the normal chemicals in there, I mean, mostly water, urea, uric acid, creatinine, the electrolytes, but then you get to the screw ups, and that's where I want to finish. Okay. Because I always like to finish with screw ups. It's just sort of my happy place to be is bad stuff. What's wrong with me? Oh, I know. I work in a hospital with COVID patients all around me. All right. Or rule out COVIDs mostly. We have some COVIDs, but some are mostly, they're just checking to see if they have it. Okay, so glucose. If I have glucose in my urine, the first thing that pops into your mind is diabetes mellitus, isn't it? Should be. Okay. Same with ketones, shouldn't it? Okay. Proteins. If I have proteins in my urine, I want you to think, first thing, I want you to think increased blood pressure, hypertension. Okay, pregnancy goes with this because there's often pregnancy-induced hypertension. All right, so the most common reason to have protein in your urine is because you got too much pressure in the pipes and it forces those filtration membranes open and the proteins come through. Okay?
I have a question.
Yeah.
How would you know if you had glucose in your pee?
Well, you're not going to know yourself until you go get it checked. This is part of just a straight out urinalysis. Now, if you are constantly drinking and peeing and drinking and peeing and drinking, you know, that polyuria, polydipsia thing, please go get checked.
You could taste it if you wanted to.
Well, you could taste it. Yes, there were urine tasters in the past. You could get a whole new job description, Clayton.
Oh.
Oh, no. Huh? All right. So proteins, I want you to think hypertension. Glucose, ketone bodies, I want you to think diabetes mellitus. Starvation, of course, will put you there. But for us, it's usually going to be diabetes mellitus, unless you see somebody who looks like they have anorexia nervosa. Okay. What if I have hemoglobin in there or erythrocytes? What's the first thing I should think of?
Oh my! Someone hit your kidneys. I mean, it's got a trauma, because if you find a blood in urine, it's a bad sign that you was injured.
An infection?
Yeah, usually it's an infection of some kind. Not usually. We don't want to jump to trauma. You're right, though, Tatiana. It's very bad if you've had trauma. But usually what we want to think is what's most common, and that's going to be either, you know, urethritis, in other words, an inflammation of the urethra, cystitis of the bladder, or nephritis. I hope not, but blood coming through. But okay, I'm going to finish with leukocyte stuff, and I want to come back to that for just a second. Okay, so bile pigments, if I see brown pee, I worry about bilirubinuria, which means I'm worried about my liver. If
dehydration too?
Huh?
Dehydration.
If it's brown as versus dark yellow, I start worrying. There's a difference. There's actually a color difference. It'll be brown.
It looks like tea.
Yes, it looks more like tea.
Yeah.
Exactly. So then I worry about my liver failing. And of course, if I see pus, I'm thinking infection. That's obvious. But I have to end with the final story. So we had this happened. We had a patient, and you have to understand that on my units, it's mostly older people. This is heart failure, strokes. They tend to be, 60s, 70s, 80s, 90s, that kind of age group. Okay, so we had a woman as a patient who was 38 years old, and the patient came, or the tech, PCT, came running out of the room saying, "Oh my God, there's blood in the hat." Okay, well, it's not a cloth hat. It's the plastic thing we put into the toilet to make sure that we collect the urine. Because when you have cardiac problems, we make sure we know how much you put out versus how much you put in. All right. So anyway, so the tech comes running out saying, "Oh my God." The nurse saunters in to the patient's room. And what's the one question she just asked this woman? Nobody. Saved her a very embarrassing call to the doctor. She asked the woman,
having your period.
"Are you having your period? Did you start your period?" And the answer was yes. It's just that we don't have these people very often. And so that just did not even cross the tech's mind. It was, "Oh my God, she's hemorrhaging." No, she started her period. Okay. So sometimes you just have to pay attention to the whole patient, not just the, "Oh my God." All right. So on that happy note of urinary problems, I'm going to bid you adieu for this part. And then I'm on for whatever questions you've got in general, because I know we got a test coming up.